All right, good evening, ladies and gentlemen. Welcome to Modeling and Optimization, real-world problems that we can use some calculus in order to optimize, which means to find max or to find minimums. This is pretty interesting stuff here. I think it is anyway. I hope you do too. All right, so we're going to start off with some kind of baselines here, some problem-solving things. So one of the biggest things in this particular section is you need to be able to understand the problem. You need to read it carefully and know that you know what you're talking about when you get to the problem. You need to develop a mathematical model, which means just write an equation. You might need to graph the function and find the domain to determine what type of x values make sense. You will probably need to find some critical points in order to find maximums and minimums of the original function. And then towards the end, you actually get to solve the model, solve the equation, and interpret the solution that you gather. Like sometimes numbers just don't make sense. If you have a length of -2, that doesn't really make sense. Or time is negative, that doesn't make sense either. All right, so these are the kind of outlines. We're going to use most of this stuff along the way today. Let's get into some good examples of what this might look like. All right, so pretty basic example from algebra. Basically, we want to find two numbers whose sum is 20. Okay, so x plus y equals 20. And then I want to see if I can find the product that's as large as possible. We'll call this product p of x. Well, I can't really graph this, and I can't really find the derivative. I can do it implicitly, but it's not really going to help us at all. There's nothing we could actually solve. So what I want to do is I want to be able to write this p of x function as one variable. So I need to know what y is. Y is actually 20 minus x. So I can now substitute into p of x. So now I get p of x is equal to x times 20 minus x. And some of you might be looking at that and go, oh, that's a quadratic. And it's a negative quadratic, which means there's going to be a maximum value, which is right. So we're going to look at p of x equals to negative x squared plus 20x. And then I'm going to find the derivative. I don't want to do this in the regular algebra way. I want to find the derivative, use my critical points. I want to know when this thing equals 0. And I get x is equal to 10. Now you have to remember, don't circle that because that's not your full answer. Your full answer is finding two numbers. You've only found one. Well, lucky for you, you know that the other number is 20 minus the one you found. So I know y is equal to 20 minus x, which is 10, which means your numbers are 10 and -10. So exciting. We just solved a really simple algebra problem using some calculus. All right, so that's kind of the baseline problem. We understood the problem, we wrote an equation, we solved it, we interpreted it. Sorry, where did I get -10 from? Jeez Louise. I am not paying attention. -10 doesn't make any sense. I didn't even have -10 anywhere. All right, 10 and 10. All right, so those are our two numbers. Let's move on to a more interesting problem, one that I really enjoy. I like this problem here. So you're going to be making a box. You're going to be given a flat sheet of tin, and you're going to cut out little X's from the side, from the corners, and you're going to bend up the sides, and I want to know how big the X should be, how big the corners should be that you're cutting out in order to make the largest volume. All right. So I hope you wrote this down because I'm going to move over to another page, a blank page, and I'm going to look at the fact that I have a 20 by 25 piece of tin. So I have a 20 by 25 piece of tin, 20 by 25. And I'm going to be cutting little X's out of the corner, little corners out. And then eventually we would fold along these sides, fold up, and create a box, an open-topped box. All right? Very basic idea, something you may have done with a piece of paper at some point in time, but very, very basic problem. And we want to figure out how long this X should be that I'm going to cut out. So we need to figure out some dimensions. Well, since we're finding volume, volume is equal to length times width times height. Well, let's just start looking at what I have. Volume that I have is, well, the length is 25 originally, but I'm subtracting an X here and subtracting an X here, which means my length is actually 25 minus 2x. And some of you might be remembering this type of problem from previous classes. Then my width was originally 20, but again, I'm going to subtract an x and an x. So I have a 20 minus 2x. And my height is going to be x because that's what I'm going to be folding up. So this is now my equation. The problem is I want to find the derivative of this, so I'm going to re-represent this equation a little bit. I'm going to bring out a 4 from a 2 from both of these, and I'm going to get, actually, let's take out a negative 4 just for the heck of it. So I can get an x. Oh, I can't take a 4 out. What am I doing? Silly goof. I can take a 2 out, but that's not really going to help me anymore. So let's just FOIL. 25 times 20 is 500 minus, let's go minus 40x minus 50x, so I get minus 90x plus 4x squared times x. And you get a really nice equation of 4x cubed minus 90x squared plus 500x. Well, in order to find maximum value, I need to find the derivative. So v prime is 12x squared minus 90x plus 500. Well, now I need to find some zeros. Well, that's kind of a pain because I don't think this is factorable. And if it was, I can't factor it quickly. So I'm going to automatically go to quadratic formula. All right, so you get the quadratic formula down. You get x is approximately equal to 3.68 or 11, actually, and 11.32. So the question is, what value are we looking at? Which one makes the correct answer here? Which one makes the maximum volume? And if you're thinking about the original problem, the graph, I'm going to have x-intercepts of 0, an x-intercept of 10, and an x-intercept of, what do we got here, 12.5? Most of you could probably graph this pretty quick and just off the top of your head. It's going to go like this. And if you notice, 11.3 is between those two values, which is going to give me a negative volume. And you could figure that out for yourself here. 11 is going to make positive for the x, negative here, and positive here. It's going to make a negative volume. So that doesn't even make sense. We do kind of want to test the endpoints just because our definition of critical points and min and max, but technically when you plug in 0, you get 0, and when you plug in 10, you get 0. Well, that's not very interesting. And you might understand that that is our domain because you can only go from 0 to 10. As soon as you get any bigger, the problem breaks down. It doesn't even make sense anymore because if you try to take 20 away from these x values, you've tried to take more than what the box had to begin with. All right, so that means x equals 3.68 kind of has to be my maximum. So 3.68. So I want to figure out what the volume is. So the volume at 3.68 is, do a little bit of calculation on your calculator. You get a volume of 820.53. And if we interpret this, this means cutouts of 3.68 by 3.68 inches and a volume of 820.53 inches cubed would be our solution. All right, pretty straightforward there. Not too much to deal with. Some of you might think that's a long problem, but I think I love this problem. It's one of my favorite problems, actually, finding the maximum volume. I don't know why it's my favorite, but it just is. All right, moving on. Not a lot of examples, but this one is going to get challenging. So now we have a rectangle inscribed under, so the word inscribed is pretty important here, under one arch of the sine curve. So hopefully you remember what the sine curve is. And we're only dealing with one arch, so let's deal with the most basic one of the arches. So let's go from 0 to 0 to pi. Be helpful if the words came out of my mouth correctly. All right, so from 0 to pi, sine does this. And you guys remember it goes up to 1. And then we have a rectangle inscribed under this particular curve. Now we're going to look at two little points here. We're going to call this point P and point Q. And we're going to let P have the coordinate x, comma, what? Well, if I plug in an x, the y value has to represent the height according to the sine curve, which means it's just going to be sine of x. Now, the coordinate of q is a little bit more challenging, but it has to do with symmetry. If this distance right here is x, so is this distance between pi and the x-coordinate of q, which means the x-coordinate is going to be pi minus x. And it's all have to do with symmetry in this particular case, and sine is very symmetric. And again, it's sine of pi minus x as the height. Well, there are some properties of sine that we got to remember. That's basically the same thing. Sine of pi minus x is the same thing as sine of x. All right, so really what we need to come down to now is we need to figure out the rectangle, really. We need to figure out length and height. Length and width, whatever you want to call it. Base and height. So we need to figure out some base and some height. Well, in this particular case, my height is pretty easy. My height is just the distance created from the x value, and that's the sine of x. So my height is sine of x. My base, however, a little bit more challenging. It's the distance from pi minus x to x. Well, distance just means subtraction. So it's pi minus x, so it's pi minus 2x. Actually, it's not that challenging at all. Which means area with respect to x is pi minus 2x times sine x. Well, that means now we can find the derivative. We want to find maximum. So this is a type of problem that will have a maximum. Okay, so we can find the derivative. A prime of x is equal to, now this, remember we got this as a product, so you have to do the product rule. So negative 2x sine of x plus pi minus 2x times the derivative of sine, which is cosine. Now, there's really no way to solve this algebraically. There probably is, but I don't know it and you don't know it. So you're going to probably have to graph this function to figure out where it's equal to 0. So while you're doing that, I'm doing that as well. I'm plugging this into my calculator. And once you get down, I've actually kind of already plugged it in. You're going to solve for the x value. And the x value that you get is x equals 0.7104, blah, 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 but I don't really care about the rest of it. 0.71. So that means we need to figure out the dimensions of the box. You got to remember that's not the actual answer. That's just the x value. So my base is pi minus 2x. So base minus pi minus 2 times 0.71, which is approximately equal to 1.72. And my height is equal to the sine of 0.71, which is about 0.65. And those are the base and the height of the rectangle that we got. And area is approximately 1.12 units squared. Not a super hard problem, but really the hardest piece is trying to figure out the length and the height from very little information. All right, but I hope this particular problem helps you with your assignment as we get going forward. Now, the next kind of stuff that we're going to be dealing with is some revenue problems, or some economic problems, rather. We're going to look at two quick theorems. I'm not going to give any examples of this because they're basically just going to be equations that you're going to be finding the derivatives of. But you kind of needed some terminology. All right, so max profit occurs at a production level at which marginal revenue equals marginal cost. Now, I think we dealt with these words a little bit earlier in one of our previous chapters, but we're going to kind of revisit them. You're going to be given probably 3 equations, maybe 2 equations, this R and the C. And R is the revenue, C is the cost, and profit is just revenue minus cost. But really the big thing that we want is marginal. And if you remember, marginal deals with the derivative. So the derivative of R with respect to X is the marginal revenue. The derivative of cost with respect to X is the marginal cost. And derivative of profit derivative of profit with respect to X is the marginal profit. All right, so those are just kind of little things that you need. They're basically going to be giving you a revenue equation and probably a cost equation, and then you're going to need to figure out when does marginal revenue equal marginal cost. And then the last thing we're going to deal with is the minimizing the average cost, and this is another theorem. And the production at which average cost is the smallest is when the average cost equals the marginal cost. So there's one little thing that you need to know, one thing we haven't done yet, on my previous page is average cost. And average cost, you know how to find averages. Average cost is just the cost divided by the number of items you produced. So if you produce 10 items, so you do cost at 10 divided by 10, that would give you your average cost of producing 10 items. That's pretty simple. So the economics problems, they're pretty good problems. They're actually pretty fun problems if you like the finding the derivatives. I like it, but that's me. Okay, so your assignment, you know, is on your pink sheet. If you don't, you can email me, you can text your friends, whatever you need to do. And I'm mentioning this again. These are some of my favorite types of calculus problems. This optimization types of problems gets you really kind of thinking about where calculus could be used. All right. I hope I didn't get this up too late for you guys to get this watched and ready for tomorrow. But I hope you guys have a good time with this type of math. Hope you kind of are interested in the stuff that we're doing here. All right, have a good evening. I'll see you guys tomorrow.